In this video, we'll take a closer look at the HEUI injector, one of the most sophisticated fuel injectors used in diesel engines. It combines electronic control with hydraulic actuation. Its key feature is the use of two separate circuits. The first is a low-pressure fuel circuit supplied by a transfer pump. The second is a high-pressure engine oil circuit that drives the pressure intensifier inside the injector. The engine control unit, or ECU, electronically controls each injection event. Inside the injector, fuel pressure can reach approximately 210 megapascals. This extremely high pressure ensures excellent fuel atomization and efficient air-fuel mixing within the combustion chamber. Let's begin by looking at how engine oil and fuel are supplied to the injectors. Let's start with the engine oil supply system. Engine oil from the lubrication system is supplied to a high-pressure oil pump. The pump is driven by the crankshaft, and its output depends on engine speed. As engine speed increases, the pump delivers more oil. The pump can raise the oil pressure from approximately 6 megapascals to as much as 30 megapascals. However, the actual pressure depends on the engine operating conditions and ECU commands. To precisely control the oil pressure, the system uses an injection actuation pressure, or IAP, control valve. This solenoid valve is operated by a PWM signal from the engine control unit. Depending on the PWM duty cycle, the valve bleeds off a portion of the oil flow, thereby regulating the pressure downstream of the pump. The oil is then delivered to the injectors through a common high-pressure oil gallery, which serves as a pressure reservoir. Now let's look at the fuel supply system. Diesel fuel is delivered from the fuel tank by a transfer pump into a common fuel gallery, supplying all the injectors at a pressure of approximately 400 to 500 kilopascals. In this system, the transfer pump is mounted on the rear of the high-pressure oil pump. At this point, both engine oil and fuel are supplied to the injectors. Now let's examine the injection process. It begins with a command from the ECU. When the ECU sends this command, the poppet valve solenoid is energized. The resulting magnetic force overcomes the return spring and opens the valve. This action is also assisted by oil pressure acting on the valve. With the valve open, high-pressure oil from the gallery flows into the chamber above the intensifier piston. The oil pressure above the piston rises to match the gallery pressure. The intensifier piston is the key component of the HEUI injector. Its upper surface area is approximately 6 times greater than the area of the plunger beneath it. As the piston moves downward, this difference in surface area creates a hydraulic multiplication effect. As a result, the fuel pressure beneath the plunger is multiplied by approximately 6. For example, when the oil pressure above the piston reaches 30 megapascals, the fuel pressure beneath the plunger rises to approximately 180 megapascals. At the same time, this high fuel pressure acts on the injector needle. Once the fuel pressure overcomes the force of the needle return spring, the needle lifts from its seat and fuel is injected into the combustion chamber. It should be noted that this injector design, as well as some early generations of HEUI injectors, such as those used in Caterpillar 3126 engines, uses a plunger geometry that produces a brief mechanical pilot injection before the main injection event. Let's examine this process in more detail. As the plunger begins to move downward, the fuel pressure beneath it rises. This initiates a brief pilot injection. The pilot injection continues until the groove in the plunger aligns with the spill port. At that moment, the chamber beneath the plunger becomes connected to the spill passage. Part of the fuel is discharged through the spill port. This causes the fuel pressure beneath the plunger to drop rapidly. As a result, the pressure falls below the level required to keep the injector needle open. The needle return spring forces the needle onto its seat, temporarily interrupting the injection process. However, the intensifier piston continues to move downward. Once the plunger closes the spill port, the fuel pressure beneath the plunger rises again. This increased pressure lifts the injector needle from its seat, initiating the longer main injection event. This design enables pilot injection solely through plunger geometry. In more modern HEUI versions, additional injection events can be performed under ECU control, made possible by the injector's faster response. When the ECU ends the injection command, the poppet valve solenoid is de-energized. The return spring forces the poppet valve closed and overcomes the oil pressure acting on it. At the same time, the drain passage at the top of the valve opens, causing the pressure above the intensifier piston to drop. The intensifier piston return spring pushes the piston back to its upper position. As the piston moves upward, the low-pressure oil above it is discharged through the drain passage into the valve compartment of the cylinder head. This upward movement reduces the fuel pressure beneath the plunger. The injector needle return spring then closes the injector needle, ending the injection event. At this point, the inlet port opens, allowing fresh fuel to enter the chamber. This prepares the injector for the next injection event. The engine control unit continuously manages injection timing, injection duration, and fuel injection pressure based on sensor inputs. Injection timing is adjusted according to engine speed and load. The quantity of fuel injected depends on the duration of the ECU control signal and the oil pressure acting on the intensifier piston. Oil pressure also significantly affects the fuel delivery